I'm Dr. D.K. Tripathi, an assistant professor in the Department of Physics under the Basic Science and Humanities Department. In the last lecture, we have learned the nanomaterials and the types of nanomaterials. We also come to know that what are the different properties of nanomaterials and what is the cause of reduction of dimensions. By reducing the dimension, what happens? So we have uh, completed that lectures with the type of nanomaterials on the basis of their occurrence. Today, we will discuss the types of nanomaterials on the basis of number of dimensions in the um, nanoscale. So the first type of nanomaterial, which is called as zero-dimensional nanomaterial. Zero-dimensional nanomaterial means its all dimensions lies in the nanometer range. That means no dimension is seen in the bulk range. So that is why the dimension is said to be zero. Zero means no dimension is in the bulk region. All the dimensions of this object or this body or this particle is in the nano range. Nano range, I told you that as per standard definition, that if any dimension of a particle or a body is lying in between 1 to 100 nanometer, then the material is said to be nanomaterial or nano structure. So here all three dimensions are lying in less than 100 nanometer or equal to 100 nanometer dimension. So here it is written D is either less than or equal to 100 nanometer. All the dimensions along the X direction, Y direction, as well as Z direction. That means all three directions. The diameter in all three directions is how much? Either equal to 100 nanometer or less than that. Now you see, if the dimension is very, very small in all three directions, then what will be the shape of the body? The shape of the body will be like a dot. The shape of the body will be like a dot, or like the pointer. You are viewing this red color point, like this red color point, but size will be very, very small. Structure will be like that, but the size will be very, very small. So that will be, the size will be like a particle. So here these are the nanoparticles, the particles whose dimensions are very, very small in the nano range. So these are the nanoparticles. The example of zero-dimensional nano material is quantum dot. What is this quantum dot? This quantum dot can be used as the artificial atom. In the scientific research, this quantum dot is used as the atom, the atom which can serve as the artificial atom, because up to the atomic we don't have anything. You just recall the experiment done by Rutherford. There the gold foil was taken, but its size was nearly more than 1,000 times or lakh times greater than the um, size of an atom. But here quantum dot size is very much closer to the size of the atom. The size of the atom is 10 power minus 14 meter. So whereas the size of the nanomaterial or quantum dot is 10 to the power minus 9. So it can be taken as the, this quantum dot can be taken as the artificial atom. Now, one-dimensional nanomaterials. One-dimensional nanomaterial means its one dimension will be seen in the bulk region. That means one dimension will be greater than, will be a bigger dimension which can be seen. That will not fall under the nano range. Other two dimensions will be in between 1 to 100 nanometer. So as one dimension will be seen to us, that is why we are naming this as one-dimensional nanomaterial. The examples are nanowires, nanorods, and nanotubes. Why these are called so? You see, the two dimensions. Suppose this X dimension and Y dimension. These two are in the nano range, so size will be very, very small in this X and Y direction, only in the Z direction. That means out of the screen of the computer, it will have length. So it will be like a rod, or it will be like a wire, or it will be like a tube. That is why, because of its size, it is called as nano rod or nano wire or nano tube. Carbon nanotube we will discuss. This is the strongest material of the world till now invented. So carbon nanotube is one-dimensional nanomaterial. Now two-dimensional nanomaterial, that means its two dimensions are in the bulk range. Only one dimension is in the nano range. This means that out of, you see, as in this figure, what happens? The dimension in the X direction is existing, the dimension along the Y direction is existing. That means we can see its X and Y dimensions, whereas Z dimension is extremely small in the nano range. That is why that is not viewed to us. This is somewhat like that, very thin slides, very thin slice of material. So these are nano fibers. Nano fibers are there. That means you can see two dimensions only. The third dimension is extremely small, which cannot be viewed to us. So here it is written that third dimension T is equal to or greater than 100 nanometer as per the standard definition. And the example of two-dimensional nanomaterial is nano coatings. If you are using, you see, nanomaterials are used as emulsions, as paints. So nanomaterials are put there. So if there will be any coating of nanomaterial, like you just recall that electroplating was done, and in the electroplating, the other material is put over the primary material. Or you have learned that silver is deposited over aluminum with the help of electricity. So that was what? That was electroplating. So here also, if we can do, we can use the nanomaterials to coat something. So its coating will be very, very small, and that will be called as nano coatings or growing of nanofilms or nanofibers. Now, three-dimensional nanomaterials. That means all the dimensions will be seen by us. That means no dimension is in the narrow range. All the dimensions are in the bulk range. Okay, so that will be called as three-dimensional nanomaterial, like colloids. Okay, milk, blood, all these are three-dimensional nanomaterials. Nanocomposites, these are also nanomaterials. So this is the diagram of three-dimensional nanomaterials, where the all three dimensions are visible to us and they are not falling in the nano range. This is X direction, this is Y direction, and this one is the Z direction. Now, let us have an idea that how they will be there. You see, if the particle is only here, that means it is not moving in any direction. If the atom is not moving in any direction, or the particle is confined in the range, in very small range of 100 nanometer in all three directions, that will be zero dimensional. If that particle or atom can move along one direction, or if it is there in the one dimension, only one dimension of it is seen, and other two dimensions are extremely small, then that will be one-dimensional nanomaterial. But if two of the dimensions, that means along the z-axis and along the y-axis, x-axis, or along the y-axis or z-axis, the material exists. So what you will get? A film, or a fiber, or a coating. So that will be two-dimensional nanomaterials. But in all three, if all three directions are there, which is greater than the 100 nanometers, so what we can say? We will call this as the three-dimensional nanomaterial. Now, quantum confinement. This is very, very important thing. You will have to know. You see, the word confinement means restriction. if a particle is confined, restricted to move in very small area, because quantization is always coming at lower level. So if in very low dimension, the electrons are confined, that means they cannot move, they don't have any degrees of freedom, then this is called as quantum confinement. They will have to move within that very region. They cannot go out of that region. That means, suppose when you are entering your college and after that the gate is locked. So what will happen? You will be confined within the college. You can move or roam within the college. You cannot go outside the college. Like that, if in a region or range, the electrons are confined, so they can move in that very region only. They are free to move in that very region. In other region they cannot go. And if that region is very, very small, then that will be called as quantum confinement. So here I have written, so if an electron is confined to move in some smaller region, then that will be called as quantum confinement. Now you see, if the diameter of the material is comparable to the wavelength of the electron, you just go to the de Broglie's hypothesis. What we know that? As per de Broglie, what he has told, that material waves are there. That means a material can behave as the wave. And that will be given by lambda is equal to h by mv, where lambda is what? Wavelength. H is Planck's constant, and m and v, momentum and mass and velocity. So lambda, that means wavelength, can be found out. That means electron, if it is particle, then at very low level, that means at nano level, it will have the wave characteristics. And at that time, if the diameter of the material, if the material is in the nano range, that is 10 power minus 9, so diameter will certainly be not greater than that. That will be 1 nanometer or 2 nanometer or 100 nanometer, like that, from 1 to 100 nanometer. That means the dimension will be comparable, nearly equal to the wavelength of the electron. Then their electronic and optical properties deviate to large extent. So what electronic and optical properties we are seeing, we are viewing the bulk of the bulk body, that will not be seen there. This is because of the quantum confinement. Electron will move within that very smaller region, and due to that their properties will be different. The properties which we have discussed last days, that the properties will be different. Why it will be different? Have you understood? The electron will not free to move. Its degrees of freedom will be ceased. So it will not be able to move in bulk range. It will be confined to very small range of nanometers. And because of that, the properties will be different. So this is because of the quantum confinement, the properties will be different. In the last class, I told you that I will make you understand what is quantum confinement. So probably all of you have understood it. A particle behaves as if it were free when confining dimension is large. Suppose the confining dimension, that means if the dimension where the electron is confined is in the micro range, or in the bulk range greater than that milli range. That means if the dimension of along x direction, y direction or z direction is the milli range, then what will happen? Particle will find sufficient space to move from here to there. So its restriction will be very, very less. There will not be very high restrictions on it. And so it will behave as that it is like a free particle. And at that time, the diameter of the particle will not be comparable to the wavelength of the electron. So in that very time, the band gap will be fixed because of the fixed energy states. Now, we have understood the band gap in the last class and before the last class. In spite of that, I thought that we should have the idea of band gap. What is band gap? You know, the separation between the conduction band and valence band. or better to say that the separation between the upper portion of the valence band and lower portion of the conduction band is called as band gap. The gap between two bands, conduction band and valence band. So this energy gap is called as, because no charge carrier is there. In the valence band, what you are getting? Holes. In the conduction band, what you are getting? Electrons. But in this region, no electron or holes are found. So that is why it is called as gap. Which gap? Gap between the two bands. So that is why band gap. Now you see what happens, that if the electrons are falling to recombine with the holes, valence band, then there will be emission. If this energy will be multiple of h nu, and if the electrons are here, suppose electrons are here, valence electrons, so what will happen? They will require this band gap amount of energy to go to the conduction band. And same thing will be there. If the electrons from the conduction band will fall down to the valence band, they will release this band gap amount of energy. So what we conclude, that the part, if the diameter of the material is not equal to the wavelength of the electron, then it will have the same band gap as the bulk body. Okay, because of the fixed energy states. These are the fixed. Valence band is what? It is a cluster of the valence levels of all the atoms which is constituting the lattice of material. Like that, conduction band is what? It is a range of energies possessed by all the conduction electrons of all the atoms of that very lattice or of that very material. So, but if the region dimension is in the nanoscale, this happens to the material if you are just squeezing its dimension to from bulk body to the milli range or micro range. But if the region dimension is in the nanoscale, okay, the energy spectrum becomes discrete. So at that time, the energy spectrum will become discrete, which results in the size dependent band gap. That band gap will not be fixed. That will change. And what will happen? It will become bigger. It will become bigger. So in the nano range, band gap becomes greater than at bulk level. At the bulk level, what is the band gap? That will not remain at the nano range. Okay, that will increase. Now you see, this is the band gap. This is showing the band gap or gap in the bulk semiconductor. Okay, whereas here the band gap of quantum well. Okay, the particle is free to move in all three possible directions here. Here the particle can confine in the two-dimensional quantum well is this. So it can move in the y direction as well as x direction. Y direction as well as x direction. Whereas this here the particle can move in all possible directions. Okay, the third axis is not shown here. In the quantum wire, what happens? The particle can move in only one direction. It can go there, it can come here, it can go there, it can come here. So that only in one direction. You have seen that quantum wire is a one-dimensional nanomaterial. And in the quantum dot, what happens? The particle is confined in all three dimensions in the 1 to 100 nanometer. That means very, very small space is there. So particle is not having any freeness to move. Particle will be confined. There will not be any, you can say that particle will not be able to move in any other direction. There will not be any freeness. Particle will be confined to a very, very small region. It cannot move. Whereas in quantum waves, particle can move in two directions. It can move from x and y direction or y or z direction or x or z direction like that. Now, two-dimensional quantum well. This is very, very important concept. And on the basis of that, we will be able to deal the other topics. So two-dimensional quantum well. Well, you know, potential well. Probably all of you have learned in quantum mechanics, uh, quantum well. Quantum well is what? If a particle is dropped in two-dimensional potential well, so that it cannot, that means its energy will be, it will have the potential energy within this range only. You just recall, TKM sir has taught you that in the class also. I will tell you how it will happen, that a two-dimensional potential well, here if minus A and there is plus A, so particle will have the potential energy in this region only. Outside these two regions, outside these regions, that means beyond these regions, its energy will be zero. Its potential energy will be zero. That is called as potential well. This seems if um, a particle is in the well, that means the potential, if particle want to escape this well, what will happen? It will have to have this amount of energy which it cannot have. So that is why quantum tunneling is there. Okay, so what is quantum tunneling? That we will discuss in the next class. Now you see quantum well concept. So that is potential well. What is quantum well? Quantum wells are ultra thin quasi 3D planes. Okay, if suppose this is a three-dimensional object. Out of this three-dimensional object, if we cut a very thin strip, okay, very thin strip, so what will happen? Its two dimensions are seen to us along the y direction as well as along the z direction, whereas x direction is extremely small, that means in the nano range. And if that is extremely small, so two dimensions are seen to us, and that is why this will be called as two-dimensional nanomaterial. Okay, and in this two-dimensional nanomaterial, the electrons or the particles which are there, they will be confined to in this two dimensions only. They can move in these two dimensions only. And in the third dimensions, the atoms will come to the surface. That means surface to volume ratio will be very, very less. And if surface to volume ratio will be less, then all the properties like optical properties as well as electrical properties will be different than the bulk body. Okay, so it's a three-dimensional, you can say that three-dimensional planes where one dimension is in the nano range and two dimensions are seen to us. You see, this is another quantum well. So what we can say that a narrow strip sliced from one of the planes, if this is one plane, okay, from this plane, if a narrow strip is sliced, that means cut out, very, you have seen the slice of the breads. So like that, bread. So like that, if we take a slice from any of the plane, then that will define the quantum wire. Okay, that will define the quantum wire. Better to say that that will define the quantum fiber, okay, or nano fiber. And if you roll down this, suppose you are rolling down it, you are dicing it, so its structure will be spherical one. Okay, and because of rolling down, the size will further decrease. And if size will be further decreased, then what will happen? It will be, you see this seat, if this is rolled down, if this will be rolled down, what will happen? The size will be further decreased. Only one dimension will be seen to us, the length direction or the height direction or the breadth direction, and other two directions will go to the nano range. Then this will act as the quantum wire. Otherwise, it is like the plane, which is, you can say that nano fiber or nano plate. Reducing the number of dimensions. Okay, now, rather than that, if we further decrease the size in all three directions, that means only one direction is with us. If we further decrease that size, so it will have the structure like zero, and that will be zero dimensional because all the dimensions will be in the nano range. If you further roll it up, in one dimension is seen, and if you roll it continuously, so after some time, what will happen? Its size will become very, very less. And if the size will be very, very less, that will be zero dimensional nanomaterial or quantum dot. So reducing the number of dimensions in this manner forces electrons to behave in more atom-like manners. So if we reduce the dimensions, then electron will be confined to very, very small range and quantum confinement will be there. And because of that, these electrons will behave as the atoms because very less number of electrons will be there. Okay, now quantum wheels may be viewed as sandwiches consisting of a layer of materials with small band gap embedded between two layers of materials with a large band gap. Now what we can say that the quantum wheel is what? You can see that these are the sandwiches consisting of layer of materials with small band gap. We can say that there is one layer and there is another layer. And these two layers are sandwiched to each other. Okay, these two layers are sandwiched to each other with a larger band gap. Okay, so band gap will become larger. You just recall that here, suppose there is suppose there is a strip and there is another strip. So what will happen? If you want to sandwich them, then what will happen? Its dimensions, the band gap will be greater. So that is why we have told that quantum wheels may be viewed as sandwiches consisting of a layer of materials. Due to that, what will happen? The band gap will increase. And if band gap will increase, then the particles behavior or the materials behavior will be different. Such a double heterostructure confines carriers into the small band gap material, thus realizing the growth direction, the particle in a box. This you have learned in the quantum mechanics, actually particle in a box or potential well. So quantum well technology allows the crystal grower who is growing the crystal for the first time to control the range. They can control the range that where the tailoring is. That means if two quantum wells are attached to each other, what a tailor is doing? Tailor is stitching the two parts of a cloth. So here also, if the band gap is tailored, okay, if the band gap is tailored, then the characteristic will be different. So the quantum well technology allows the crystal grower for the first time to control the range, depth, and arrangement of quantum mechanical potential wells. This is very, very important thing. A quantum well is a potential well with only discrete energy values. This is to be taken in mind. The classic model used to demonstrate a quantum well is to confine particles. I told you that the main aim is to confine the particle in a very, very small range so that their properties can be controlled by from outside, because maximum of the electrons will come on the surface, and we know that any properties of a material is due to the electrons. Okay, so electrons number can be controlled, electrons movement can be controlled, and because of that their behavior can be controlled. So the classic model used to demonstrate a quantum well is to confine particles which were initially free to move in 3 dimensions. Okay, particles were already free to move in 3 directions in any bulk body. But what you are doing? You are sticking, you are just confining its movement in only 2 directions only. In 3rd direction, it cannot move. So you are imposing a constraint that that particle will not move by its geometry. If you are reducing its size, that means you are giving a constraint in the third directions that electron cannot move in 3rd direction. It will move in the 2 directions only, and because of that its properties will be substantially changed. So the effect of quantum confinement takes place when the quantum well thickness becomes comparable to the de Broglie wavelength of the carriers. What are carriers here? Either electrons or holes in the case of semiconductors, or only electrons in the case of conductors. They are controlling, they are the carriers, so they are controlled. if the wavelength, their wavelength of holes or electrons is comparable to the thickness of the quantum well, then properties will be different, leading to energy levels called energy subbands. So energy levels will be modified and these will be called as energy subbands. That is, the carriers can have only discrete energy values. A large number of electronic quantum well devices are deployed nowadays. On the basis of this quantum well concept, a large number of electronic devices has been developed and they are used. These devices are used in lasers, photodetectors, modulators, and switches. Compared to the conventional devices, what happens that quantum well devices are much faster. This is their, you can say that merit, that they are much faster, operate much more economically. That means the cost is small and are a point of incredible importance to the technological and telecommunication industries. These quantum well devices are replacing many existing devices as well as many circuits or electrical components in the electronic devices. So quantum mechanics, now what happens actually there? Here quantum mechanics is used, and that is why the manufacturers are using this quantum mechanics, that means quantum well concept, for developing the lower dimensional objects. How? By squeezing one of the side from 3-dimensional. They are making the 2-dimensional nanomaterial, and this 2-dimensional nanomaterial will have different property than its 3-dimensional behavior. How? What properties will be changed? The properties like density of state will be changed. Okay, so after determining what layer thickness induced what energy level, researchers can design the precise characteristic of a material. It is very important. You see, after determining what layer thickness induces what energy level, by in reducing the dimension to the nano range, what we are doing? We are trying to know that how their energy level will be changed. If suppose a material size is decreased to 1 nanometer, its property will be different than if the material size is 50 nanometer. So the researchers or the scientists or manufacturers are knowing with their rapid growing that rapid growing of the nanomaterials, they come to know that which thickness of the layer induces what energy level and how much band gap can be increased, and because of that which precise characteristic of the material can be built up. So they are controlling the whole characteristic of the material during the manufacturing. By knowing this, electrons are not really confined to physical barriers. To trap electrons, one need only sandwich material. If you want to trap the electrons, then you will have to sandwich material. Otherwise, electron cannot be confined. You cannot control electron. The physical thing is different. Typically, a crystalline semiconductor filled with low energy electrons between two slices of semiconductor with higher energy electrons. Any electrons in the lower energy slice will confined, unable to cross the barrier between the two different semiconductors. If the barrier is sufficiently thick, this is quantum tunneling. So here you will have to give the energy, or you will have to have the quantum tunneling. Okay, so you have had this concept in quantum mechanics. In turn, heterostructures are formed from multiple heterojunctions. So in the next class, we will discuss the nanowires and quantum wires, or nanowires or quantum wires, and quantum dots. Now, these are the references. You must go through all of them for having the better knowledge. And lastly, thank you.